Hi, my name is dr. Ahmath. In this video lecture, we are going to solve an example to construct the complete solution of a system of linear equations. So let's say the coefficient matrix for the system of linear equations is given like this, which has the 3 rows and 4 columns. So we need to solve the system. So please note that the matrix has 4 columns. And every column is going to refer to one of the unknown variables. So the first column is going to refer to the first variable, second column to the second variable, third column for the third variable, and fourth for the last fourth variable. So essentially, the number of the variables is the number of the columns of your coefficient matrix. So that is why we are going to have 4 components of this vector or the solution vector. And please know that when you multiply the matrix A, which is this 3 by 4 matrix, to this vector X, which is 4 by 1 vector, the multiplication is going to give you 3 by 1 vector. So essentially, the right-hand side part is the 3 by 1 vector, and its components are equal to the 4, 2, and 10. So the number of the solutions for any system of linear equations can be like the unique solution, or it is possible that there are no solutions, or it is possible that there are infinitely many solutions. Many solutions. So I think our case is the last one where our system is going to have the infinitely many solutions. Because when the system has one solution or no solution, it is more or less easy to construct the solution space. And it's more or less difficult to construct the solution space when there are infinitely many solutions. So let's try to solve this. So the algorithm of constructing the complete solution for this kind of systems is the following. So the first of all, we need to create the augmented matrix by putting the coefficient matrix A and the right-hand side vector B and bring this matrix to the reduced row echelon form, essentially to the form of the R, so which is going to be the reduced row echelon form of this matrix A, and obviously this B is going to change and it's going to be another vector D. So obviously this augmented matrix, the initial one, is going to be different from this one, so they are different. But what is common between them is that they have the common solution. So they have the common solution. So essentially the solution of the first system of this one is the same as the solution of this system. So that is why it is legal for us to bring the matrices into the row echelon form. So once we found this, what we're going to do is we're going to check the number of the solutions, and if the system has infinitely many solutions, then we're going to find the particular solution. Oh, so in the second step, we are going to identify the free variables and the pivot variables. So essentially the columns which does have the pivots are going to be called the pivot columns or the pivot variables. And the columns, analogously, columns which don't have the pivots are going to be called the free variables. So step number 3 is we are going to find the particular solution by setting all the free variables to be equal to the 0. So the free variables are going to be set to be equal to the 0. Then we are going to find the spatial solutions. And the number of the spatial solutions is going to be equal to the number of the free variables. And at the end, we are going to simply combine them. So the complete solution, or the space of all of the solutions, is going to be the span of all possible linear combinations of the spatial solutions, and so on, and n, plus the particular solution, x particular. Okay, so let's perform all of the steps for the given system. So I'm going to first of all create the augmented matrix. So in order to do this, I'm going to copy all of these numbers. It's like 1, 2, 1, 0, 2, 4, 4, 8, 4, 8, 6, 8. And I'm going to also copy the b vector, which is 4, 2, and 10. So please note that we need to, in order to bring the row this matrix into the row echelon form, we need to go through from the first row, which is the pivot, and eliminate all the entries below this. In order to do this, we multiply the first row to the -2 and add this to the second. We multiply the first row to the -4 and add this to the third row. Okay, if you do this operation, what kind of matrix we get is essentially it's going to be a 1, 2, 1, 0, 4. So if you multiply all of the entries on this row to the -2 and add this to the second, what you get is essentially it's going to be 0 here. So it's going to be 0. So 1 times the -2 plus 4 is going to be 2. 0 times the -2 plus 8 is going to be 8. 4 times the -2 is going to be -8 plus 2 is going to be -6. Now I'm going to multiply all of these entries to the -4 and add this to the last one. It's going to be 0 again. So the 2 times the -4 is -8 plus 8, it's 0. So it's going to be 2 here, then 8, and -6. Okay, so I've got the pivot in the first column. In order to get the pivot in the second column, we need in the second row, sorry. In the second row, we need to again choose the first non-zero entry and eliminate everything below this. In order to do this, we multiply the second row to the -1 and add this to the third row. And if you do this, what we get is essentially it's going to be 1, 2, 1, 0, 4. 0, 0, 2, 8, -6. 0, 0, 0, 0, 0. Okay, so this matrix is already in the row echelon form. And in order to bring this into the reduced row echelon form, we need to perform a couple of more operations. So namely, we need to make this 2, this pivot 2, to be equal to the 1. And it is easy to do, which we can just multiply the second row to the 1 over 2 and get this 2 to be equal to the 1. It is going to be 1, 2, 1, 0, 4. 0, 0, 1, 4 minus 3, 0, 0, 0, 0, 0. Please note that this matrix is in the row echelon form now. It is not reduced row echelon form since some of the columns which have the pivots, so the first column have a pivot and the third column have a pivot, do not have zeros everywhere else except the pivots, right? So we need to eliminate the entries above the pivots as well. So in order to do this, I'm going to multiply the second row to the -1 and add this to the first one. If you do this, what you get is essentially it's going to be 1, 2, 0, -4. So -3 plus 4, it's going to be 7. On the second row, we're going to have 0, 0, 1, 4, -3. And the last row is going to be the same. 0, 0, 0, 0, 0. Well, this is now in the reduced row echelon form. Row echelon form. And this matrix is written in the form of this R matrix, right? And here we've got this D vector. And the solution of this matrix is going to be the same as the solution of the original matrix. And if you remember, the step number 2 is we need to identify the free variables and the pivot variables, right? So what I'm going to do is I'm going to go through all of the 4 columns of this matrix R, and I'm going to find the columns which have the pivots. You see the first column and the third column have the pivot. So that's why x1 and x3, the first and third variables, are going to be the pivot variables, or they're so-called dependent variables. And the second column here and the fourth column do not have the pivots. So that is why x2, the second variable, and the fourth variable are going to be the free variables. So it is important for us to identify the free variables and the pivot variables in order to construct the particular solutions and the spatial solutions. So now we would like to construct a particular solution, x particular. In order to do this, we're going to set all of the free variables to be equal to the 0 and solve the system Rx to equal to the d. So essentially, the steps are x2 to be equal to the x4 to be equal to the 0. Then we need to solve our x is equal to the d system. So what is the Rx is equal to the D system is that? So x1 plus 2x2 minus 4x4 is equal to the 7, right? So I've just copied this very first row. And if you copy the second row, it's going to be x3 plus 4x4 is equal to the minus 3. So we are going to solve the system by setting x2 and x4 to be equal to the 0. If you set this, what we get is x1 is equal to the 7 from the first equation. x3 is equal to the minus 3 from the second equation, right? So we've got this particular solution. X particular is going to have four components, right? So it's going to have the x1, x2, x3, and x4. And x1 is going to be equal to the 7, x2 is going to be equal to the 0, x3 is going to be equal to the minus 3, and x4 is equal to the 0. So this is going to be our particular solution. Now, now we need to find the special solutions. And the step number 4, we need to find the special solutions. And again, so the number of the special solutions is going to be the same as the number of the free variables. So we've got the two free variables, x2 and x4, right? And the number of the free special solutions, s1 and s2, is going to be the same as the number of the free variables. So we first of all are going to find the s1, the first special solutions. In order to do this, we set x2 and x4 to be equal to 1 and 0, the first column of the identity matrix. So this is the first column of the identity matrix, which is 2 by 2. Then we're going to plug this into the Rx is equal to the D and solve this. Oh, sorry, Rx is equal to the 0 and solve this. It's important that the right-hand side part is going to be equal to the 0, not the D. So this system is, so when you find a particular solution, you find Rx is equal to the D, and when you find a special solution, you solve the Rx is equal to the 0. So what is our system? Rx is x1 plus 2x2 minus 4x4 is equal to the 0. It's really important because so it's confusing sometimes. So it should be equal to the 0 here. And the second equation is x3 plus 4x4 is also equal to the 0. So I'm going to put this with a different color in order to emphasize this. So this is equal to the 0, and the second equation is also equal to the 0. I'm going to set x2 to be equal to the 1, and x4 is equal to the 0, and try to solve this equation. It's going to be x1 plus 2 times the 1 minus 4 times the 0 is equal to the 0. x3 plus 4 times the 0 is equal to the 0. From here, it is easy to solve that x1, to see that x1 is equal to the minus 2, and x3 is equal to the 0. So what we've got the special solution, right? The special solution is going to have all of these solutions, x1, x2, x3, and x4 together. x1 in this case is going to be minus 2, x2 is equal to the 1. We set this to be equal to the 1, right here. So x2 is equal to the 1 here. x3 is equal to the 0, and x4 is equal to the 0. Well, this is the first special solution only. And now we need to find the second special solution. So in order to set the second special solution, find the second special solution, we again get the free variables x2 and x4. If you remember previously, we set x2 to be equal to the 1 and x4 to be equal to the 0. I'm going to now set them to be 0 and 1. Again, because this is the second column of the identity matrix, which is 2 by 2. Then again, we are going to plug this into the system, Rx is equal to the 0, and solve this. So let me emphasize here that Rx is equal to the 0 system is this one. So I'm going to just copy this, x1 plus 2x2 minus 4x4 is equal to the 0. x3 plus 4x4 is equal to the 0. Please note that you have to solve Rx is equal to the 0 system, not Rx is equal to the D, as we did to find a particular solution. So I'm going to set x2 to be equal to the 0, x4 to be equal to the 1, and try to solve the system. So in this case, it's going to be x1 plus 2 times the 0 minus 4 times the 1 is equal to the 0. x3 plus 4 times the 1 is equal to the 0. From here, it is easy to see that x1 is going to be equal to the 4, and x3 is going to be equal to the minus 4. Well, the second special solution is now going to have the four components x1, x2, x3, x4. And this is going to be equal to x1 is equal to the 4, x2 to be equal to 0, because this is we decided to be equal to the 0. That's 0, x3 is minus 4, and x4 is equal to the 1. Well, they found now all the components are to construct the space of the complete solutions. So in step number 5, in the last step, we are going to construct the space, of complete solution. Complete solutions. And this is how it works. So basically, the X complete is going to be the span of the special solutions, S1 and S2, plus the particular solution. Okay? So in particular, we can write this down. The span means all possible linear combinations, right? The special solution was 1 was minus 2, 1, 0, 0 is going to be multiplied to some parameter t1, plus the second special solution 4, 0, minus 4, and 1 is going to be multiplied to the another parameter t2, plus the particular solution was equal to the 7, 0, minus 3, and 0. Well, by choosing, so this is going to be for any values t1 and t2 from the set of real numbers. So essentially, it has two parameters, right? So by just choosing a different values for the t1 and t2, you can construct lots of solutions. For example, you can set t1 to be equal to the t2 to be equal to the 0. Then one of your solutions is going to be equal simply 7, 0, minus 3, and 0. And this is going to be one of the solutions. If you set t1 and t2 to another values, you're going to get a different solution. So let's check whether this is the proper solution or not. We can simply check this by multiplying this to the matrix A and see whether this is going to be equal to the B factor or not. So 1, 2, 4, 2, 4, 8, 1, 4, 6, 0, 8, 8 is going to be multiplied to this vector 7, 0, minus 3, 0. I'm going to do this in this way. So if you remember, we can combine the columns of this matrix A, right, by multiplying them to the corresponding constants of this vector x. So essentially, the first column is going to be multiplied with the first entry, second column with the second entry, the third column with the third entry, and the last column is going to be multiplied with the last entry of this vector. And if you see, so the two of this four vectors, the components of the vector x are simply equal to the 0. So it is just enough to combine 1, 2, 4 with the 7 and add this with the combination of the 1, 4, 6 with the minus 3. So let's combine them. So it's going to be 7, 14, and 28 plus minus 3, 12, and minus 12, sorry, and minus 18. And if you subtract, what we get is essentially the vector 4, 2, and 10, which is actually the same vector as the B vector, which was given initially. So, well, this is the valid solution, and you can construct all the other solutions by just assigning the different values for the T1 and T2 as we did here. Well, this is how we need to construct the complete solution for the system of linear equations, which has infinitely many solutions. So I hope this video was helpful for you. Thank you very much.